Conditional probability and the intersection of events. Now, the conditional probability is based on finding the probability of an event given another. So the key thing is you're given another. And the way that that's going to be notarized or noted is with this. So when you see this, what this means, or how you say it, say this is the probability of A given B. That's how you would say it. So when you read this first example, find the probability of drawing an ace from a standard deck of cards given a red card. Now there's several ways of doing this, but here's the way I would like to do it. Well, first off, let's write down the notation. We're going to say probability of drawing an ace given a red card. A lot of times it's easier just to think about it. So let's start with the red cards. How many red cards are there? There's 26 red cards total. So we're going to start where, so that means we're only going to look at the 26 red cards. Add those 26 red cards. Out of those 26, how many are aces? Well, there's 2. And that's what you're thinking. Out of those 26, 2 are aces. So what that is, what that conditional probability is, out of the 26 total that are red, 2 of them are aces. So 2 out of 26 will be an ace, or you have a 2 out of 26 chance of drawing an ace, given the fact that you're only drawing from the red cards, which reduces down to 1 over 13. Now we could use this formula to also do it, and you may or may not want to, but if we were to use this formula, the best way to look at this formula, probability of A given B, is to recognize that this number means the number in the intersection of the two divided by the number in the given portion. So if you don't think of it like that. So if you're looking at a red ace, that's what that means. A would be that ace, and B would be the red. So how many red aces do you have? Well, you have 2. If we're doing the same example. 2 red aces. And then since we're given red cards, how many red cards are there? 26 red cards. So that's kind of what this notation means. It's the intersection of the two events. So you have an ace and red, so it's red aces. There's 2 of those. Divided by the given event, and you're given the red cards. How many red cards are there? 26. So it's kind of a way to think about it. Good example to use, I guess. So let's just look at this example. Maybe as we do more examples, it'll make a little bit more sense. A lot of times, the formulas in this section you really don't have to use. You just gotta know what they mean. This is probability of A given B. The key word is given. So like on this example, it says if we select a graduate who was offered between $40,001 and $45,000, what is the probability the student has a degree in the health fields? So basically what we're doing is we're finding the probability a student has a degree in health. I'll abbreviate it. Given, that means given. Given what? Offered. I'm just going to abbreviate a little bit. Offered between $40,001 and $45,000. So let's start with the given. Remember, this is the given portion. And that's what's going to go down here. So what goes up here is the number of people who are who have a degree in the health fields. And or intersection and offered ... divided by the number who were offered 40,001 and 45,000. Looks complicated, but it's actually really not. I'm just using some wording so to help you out a little bit. Maybe the wording will actually cause you problems. I don't know. Hopefully they'll help you a little bit. So when you're doing these given probabilities, what it's looking for is where the two events intersect. And so we have the health fields here, and we have the 40,000 to 45,000 there. The health fields and 40 to 45,000 there. So where do they intersect? They intersect there. So that means that where the two intersect is the numerator of our probability, which is 3. And then we always divide by the given. That's the main thing to remember, divide by the given. Well, the given is offered between 40,001 and 45,000. So this is the given. And so if you keep on going down, you'll see the total is right there. So the total number of people who were offered between $40,001 and $45,000 is 15. If you add these numbers together, 1, 2, 3, 4, 7, 8, it does give you 15. So it's 3 over 15, which reduces down to 1 over 5. That's your probability, which is the same as 0.20. If you want to keep on going, the reason why I keep on going in some cases is because I don't know how the questions will be worded. So this is in case you're asked for the fraction or the decimal or the percent. Yeah, I mean the same thing. Now let's move on to probability of the intersection of events. Now this formula is the exact same formula as the previous formula. It's just being rearranged. And what it basically means is, if you're asked to find the probability of events that intersect, what you do is you find the probability of the first one, and then the second probability will be based on what happens from the first one. So let's do an example. Suppose 2 cards are drawn at random from center deck of cards without replacement. That means I'm going to take a card out, and then I'm going to leave it out. So the probability of both are aces. So here's what we're doing. So we're going to find the probability of an ace and an ace, or probability of an ace, or I could just do ace 1 and ace 2. Ace 1 intersect ace 2. Now I'm not going to use that notation. I'm going to use just some basic probability and just some I'm thinking about it. So start with the probability of drawing an ace 1. So how many aces are there in the standard deck of cards? Well, there's 4. Out of how many cards total? 52. 4 aces, 52 total cards. And then, anytime we do probabilities of these intersections, this is always multiplication. Or is addition, and or intersection is always multiplication. So for the second one, or second probability, we're going to find, I'm going to use the notation here, same notation. I can say find the probability of ace 2 given I've already drawn ace 1. So let's think about what that means is, I have 52 cards. Out of those 52 cards, 4 are aces. Now what we're saying is, I've already drawn an ace from the first event. So when I draw an ace, that means there's 3 aces left. 3 aces remain. Got that? Out of, remember, I've taken an ace out. Well, so when I draw an ace, ace is gone. 1 ace is gone. 3 aces remain. Since there's 1 ace left or taken out, that means there's 51 cards that remain. So what that means is, I did all that wording just to say that when you draw an ace for the first event and you take it out and you don't replace it, that's what that means. With that replacement, there's how many aces left over? 3 aces remain. Out of how many cards that remain? 51 cards remain, or total cards, however you want to write it. So essentially all you're doing is you're taking 4 out of 52 times 3 out of 51, and you're multiplying those together, and then going to convert it to I'm going to convert it to a basic fraction. And what I'm going to do is I'm going to take my calculator, because I like my calculator, and I'm going to actually put these in parentheses. 4 divided by 52 times 3 divided by 51, or I could just multiply the top and get 12 over something, or just hit math, enter, enter. And the good thing about this calculator is it reduces everything. So 1 over 221. Now if I don't have a graphing calculator, I'll have to do 4 times 3, which is 12, over 52 times 51, which is 2,652. And then find numbers that divide into 12 that also divide into 2,652. It just so happens that 12 is such a number. So 12 goes in 12 once. 12 goes into 2,652 221 times. But the graphic calculator will do it all for you. So there's your answer. So with that replacement, probability of the first event, take that out. What's left over will be the probability of the second event. Now that example had an intersection of events. Sometimes they don't have any they don't have any intersection events. They're totally independent. So in that case, you just multiply them together. Once again, the intersection symbol upside down U means and. That's the intersection. So for example, we have 3 fair coins are tossed. Those are 3 totally separate events. One coin will not affect the other coin whatsoever. So these are definitely independent. When you flip a coin, it's not like the aces. If you draw an ace out, that means that affects how many aces remain. Now these are totally independent. So you could do it like this. I'm going to do it the way that I've done it in previous videos if you've seen those. I'm going to use my tree diagram. We're going to just do a tree diagram based on 3 coins, which when they can land heads, tails. And if they land, first one lands heads, it could be heads or tails. If it lands tails, it could be heads or tails for the second coin. And so you just keep on expanding the branches. Hopefully you've seen other videos that I've made. I'm just trying to show you that maybe there is a faster way, or maybe there's a longer way that you want to do. And if I list those down the branches, I have heads, 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 tails, heads, tails, heads, and heads, tails, tails. And then I have tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. And what I get is I get 8 total. And we want all coins landing heads up. And there's only one probability for that. So that's the answer to our probability. All H's. 1 out of 8. Now, there's probably an easier way. That's the reason why these formulas are created. So we can do it like this. If you read this down here, that the first coin lands heads up, and the second coin lands heads up, and the third coin lands heads up. So what that is, I do heads, probability of heads, times probability of heads on the second coin. This is heads 1, first coin, heads 2 on the second coin, and then a third heads on third coin. So these are 3 totally independent events. So what's your probability? And this should be easy now. Got that? If you do a single coin, how many ways can a coin land? There's 2 ways it can land. How many ways can it land heads up? 1. And the same thing for the second coin. The same thing for the third coin. When you multiply that out, 1 times 1 times 1 is 1. 2 times 2 is 4. 4 times 2 is 8. You tell me which way is easier. I know which way I think is easier. I think this way is a lot easier than that. But like I said, whenever in doubt, maybe I didn't say that in this video, but I'm going to right now. Whenever in doubt, draw it out. Or tree diagram. If I ever say Venn diagram when I mean tree diagram, forgive me. Now here we go. We're going to do some examples that are going to apply some of this. How many examples do I have here? I have 3. So we're going to say, suppose a bag contains 4 oranges and 5 apples. And we're going to draw a fruit from the bag, not replace it, and then a second fruit is drawn. So we're going to find the probability of an apple and then an orange. So, probability of an apple and an orange. When that says and, that's an intersection, and I know immediately that that's multiplication. Now these are independent events. Or they could involve some intersection of events. It just depends on if they're replaced or not. So this one is not replaced, so it's like an intersection. An apple and then an orange. Okay. So don't worry too much about this notation. I'm just showing you where you could use it. So here we go. We have 4 oranges and 5 apples. That's 4 plus 5, which is 9 total. 9 total. 9 total fruit. So what's the probability that an apple is drawn? Well, there's 5 apples. I have a total of 9 fruit. So 5 out of 9 goes there. And we don't replace it. So when you don't replace it, there's how many fruit left over? There's 8 fruit left over. And how many of those are orange? 4. Did you catch that? That's not replaced. It means once you take out a fruit, 8 left over. That's what this given stuff means. 8 remain. And 4 of those are oranges. So then you multiply the cross or reduce first, however you want to do it. Use a calculator. It doesn't matter to me. 4 are actually going to both of those. 4 are going to 25 times. And 4 are going to 72 18 times. So there's your answer. Or you can use the decimal. Now we're going to do part A again, but this time we're going to do replacement. What that means is these are 2 totally separate events. Because we're replacing them. One doesn't affect the other. So what's the probability of an A is drawn? Or an apple? Well, we have, once again, this is with replacement. You're taking it out, putting it back in. So probability of an apple is still going to be 5 apples out of a total of 9 fruit. Then we're going to put it back in. Once you put it back in, there's 9 fruit. See that? And 4 of those are oranges. See that? See the difference? Once you put it back in, we still have 9 fruit total. So now we multiply straight across. 5 times 4 is 20. 9 times 9 is 81. That does not reduce. And we're done with that one. Then we got 2 different questions here. Find the probability that 2 apples are drawn without replacement, and then again with the replacement. So let's do without first. So that's an apple and an apple. So an apple and an apple. So I'm not going to use any kind of notation as far as this up here. I'm just going to think about it. That's probably the best way of doing it. Find the probability of 2 apples is an apple and then an apple again. Without replacement. So how many apples are there? Once again, there's 5 apples out of 9 fruit. So for the first one, 5 out of 9. So without replacement, that means we have 5 apples out of 9 fruit. When we take one out, there's 4 apples that remain and 8 fruit that remain because we're not putting it back in. See that? Once you take one out, because we're saying that we had a successful draw on the first event, we're not going to put it back in. So that means you have 4 apples that remain. out of 9 fruit that remain. And then once again you multiply it straight across, 20 over 81. We're done with that one. Now with the replacement, you have 5 apples total out of a possible 9 fruit. Draw one out. We're going to put it back in, which means you have 5 again out of 9 fruit again. 5 out of 9. So then once again, you multiply straight across. 25 over 81. That with and with that replacement is a big deal, so make sure you take note of that.